All right, we're gonna go ahead and get started. Again, I have a certain place that I want to get to, and I'm hoping that we can get there and then have a little bit left to do tomorrow. 12.1 inference for linear regression. So we're going back to a little bit more of the regression lines, but it's the first couple examples are not that bad. The worst thing is you have to remember a new way to check conditions. Okay, but they give you an acronym for it and it's not terrible. So for sampling distributions of a slope, so this is the difference. We're doing sampling distributions of a slope. Choose an SRS of n observations, x, y, from a population size n with least squares regression line. Then that line is predicted y equals alpha plus beta x. Let B be the slope of this sample regression line. Then the mean of the sample distribution of B is mu base B equal to beta. The standard deviation of the sampling distribution of B is this formula. As long as the 10% condition is satisfied. And remember, we do the 10% condition to make sure that we can find the standard deviation. And that is that the sample size is less than or equal to 1/10 of the population. The sampling distribution of B will be approximately normal. If the values of the response variable y follow a normal distribution for each value of the explanatory variable x. And this is the normal condition. So the next page is going to tell us how to check conditions for regression inference. And the acronym for that is LINER, L-I-N-E-R. Suppose we have n observations of an explanatory variable x. And a response variable y. Our goal is to study or predict the behavior of y for given values of x. So this is quite a bit to write. I'm just going to forewarn you, but it's explaining exactly what these things are. Okay. So linear, the actual relationship between x and y is linear. For any fixed value of x, the mean response, and that's mu sub y, falls on the population That population is the true regression line. So mu sub y equals that alpha plus beta x. Remember the ways that you can tell if it's linear. The biggest way that you can tell if it's linear is to look at the residual plot. And if there's no clear form in the residual, you know it's linear. And that's exactly what you would state. So when you start these and you test those conditions and you're looking for linear, check out the residual plot. No clear pattern in the residual, assume linear. Okay. Independent. Individual observations are independent. Of each other when sampling without replacement. And it's still the 10% condition. There's a couple ways that you're going to tell if it's normal, but they're going to give you graphs. A lot of times they'll talk about the histograms. So if the histograms are single peak, no skewness, no gaps, no outliers, then you know it's approximately normal. Okay, if we're doing our own, we're doing box plots. Same thing. Okay, so you already noticed. For any fixed value, of x, the response y varies according to a normal distribution. And again, it's the same normal as always. Okay, we're going to check that graph and make sure that there's no skew, no strong skew, and no outliers. So this one is the weirdest one, the equal SD. You want the standard deviation of y same standard deviation. Remember that's population standard deviation, but we're just using it for standard deviation this time. Is the same for all values of x. So again, this one you can look at the residual plot and you want to make sure that they're pretty much the same distance from the residual line at 0. And we'll talk about that in just a minute. And then the last one is random, and that's normal. That's the same thing that we've been doing. The data come from a well-designed random sample or randomized experiment. All right. So now we're going to get one to check those conditions, an example to check those conditions. So it says, Miss Barrett's class did a variation of the helicopter experiment on page 738. Students randomly assigned 14 helicopters to each of the 5 drop heights, 152, 203, 254, 307, and 442 centimeters. Teams of students released the 70 helicopters in a predetermined random order and measured the flight times in seconds. The class used Minitab output to carry out a least squares regression analysis for these data, a scatter plot and a residual plot, plus a histogram and normal probability plot of the residuals are shown below. So there's all of those. This is the scatter plot. This is the residual. This obviously is the histogram. And this one is the normal probability plot. Right. Check whether the conditions for performing inference about the regression model are met. And remember, this is the one that we just did. So this is that liner. For L, we want to make sure that it is linear. And I told you the one place that you really want to look is the residual plot. And this has no clear pattern. Like it's not a U shape, it's not a line, it's not anything. It's just random scatter. And I know that they make vertical lines, but it's still not a pattern. Okay. So this one, the residual plot shows no clear pattern. For right now. If they don't, can you make them? Yes. Okay. Because they gave you the actual scatter plot, you can see that in the scatter plot, it is linear. It's increasing. You can see that it's as X increases, Y increases. So this is just, this is good. This would get you your answer. Okay. But what if you only have the scatter plot? So if we have the scatter plot, it shows a linear relationship. Again, it doesn't matter which one you use, but those two are the ones that are really important in talking about whether it's linear or not.
So the residual doesn't need to have a.
No pattern.
Okay,
No
and
pattern.
The scatter plot needs to be linear.
Yes. The pattern needs to be in the scatter plot, but not in the residual. Okay. All right. So I is it independent? So what did they do? I'm just going to go ahead and put this in here. Since they released in a random order, and none of the helicopters were used twice, one result does not affect the other. Right. Then, as a side note, there's no 10% rule because no random sample. They took all of them. They didn't sample them. Right. And it's whether it's normal. And again, we're going to check that histogram or we're going to make our own box plot. Whatever you want to do is fine. This histogram is bell-shaped. and single peaked. Which means there's no skew or outliers. Remember, that's the same thing we've always been looking for. And then the other thing that you're going to look at is the normal probability plot. Is linear. If it is linear, you know that it's a normal. And we don't have any skew in it. So we saw these a while back and they were really curved on the end and then they became linear. So that curve is that skew, okay, that left or right skew. This one doesn't have that curve. It's pretty much a straight line the whole way. E is the equal SD. I'm going to go ahead and write this down and then I'll explain it. The residual plot shows similar scatter. About residual equal to 0 line. And if you look, sorry, if you look at your residual, and I'll slide it down in a minute and show you. If you look at this line, they're pretty much equal. These are equal. These are equal. This one is a little bit weird, but these are also pretty equal. So what you're looking at is that they are, it's the same scatter based on this 0 line right here. So highest and lowest is pretty much the same. Highest and lowest is pretty much the same. Same here. This one is the one that's a little bit different. And then this one's a little bit different, but it's not enough to freak out because it's still within the realm of these as well. Okay. So this one drops higher and lower than all the rest if we're looking horizontal. Does that make sense? All right. So for the 152 height, the 203 height, the 254 height, and the 442 height.
Where are you getting those numbers from? Like, how do you see them from the graph?
Okay, so first of all, they told you what the heights were right here. So that's
Yeah, I got that part.
So then here, this is 150. So this has to be the 155. I mean, the 152. You see what I'm saying?
Yeah, sorry, I thought those numbers were decimals down there.
No, no, no. And these are all, these are the each one, the helicopters that were dropped from that height. So 14 dropped at this height, 14 at this height, 14 at this height, so on and so forth. All right. It varies more at the 307 drop height. Okay, so we're gonna hold on to that for a minute. It's not enough to worry about, but that may be one thing that would cause this to fail. Okay, but it's not big enough to worry about. It's kind of like the strong skew versus the moderate skew. Okay. And then random, just like normal, the helicopters were random assigned. To drop sites. Or you could even say drop heights, it doesn't matter.
Well, we have like this much for like everything we do.
Now, remember what I told you, this is one too many, okay? So you can either use the residual or you can use the scatter plot, it doesn't matter. I would suggest on the AP exam, probably want to say as much as you can, but be careful because if you say too much, you can get points off for that too. because you might say something wrong. That's the only thing I worry about. Do what?
There's so many.
Sometimes they are. And then in the independent, we only had to write this because we didn't have random sample. If we have random sample, you're just checking the 10% condition. Okay. So normal, no, we don't have to do that. What you can say is what we've always said, no skew or outliers, assume normality. Yep. So I just wrote a lot so that when you go back and look, you can see it. And then with the equal distance, again, you can just say that similar scatter about the residual. I mean, that's really it. And then your random assignment is the same thing as normal. Yeah, so don't freak out too much about it. All right, T interval for the slope. When the conditions for regression inference are met, a C% confidence interval for the slope beta of the population true regression line is B plus or minus T star standard error of B. In this formula, the standard error of the slope is the standard deviation, the sample standard deviation, square root n minus 1. In all the formulas that I have, or all the work that I have today, you do not use these formulas in. Okay. Like this one and the other one that I gave you with the standard deviation. And T star is the critical value for the T distribution. Watch this one right here. Degrees of freedom this time are n minus 2. Having a C% of its area between negative T star and T star. All right, that's all on this page. We're gonna flip it over and do an example. Still talking about the helicopters. Earlier, we used a Minitab to perform a least squares regression analysis on the helicopter data from Mrs. Barrett's class. Recall that the data came from dropping 70 paper helicopters from various heights and measuring the flight time. Some computer output from this regression is shown below. We checked the conditions for performing inference earlier, so we don't have to perform those anymore. We don't have to do the liner anymore. So A says give the standard error of the slope, standard error of B. Interpret this value in context. So you just need to remember where to find it. To find the standard error of B is going to be this value right here. We're not looking at the constant row at all. We're only looking at the drop height row. And we're looking for standard error. So drop height and standard error. We'll have another example like this. That's where you're going to look for that, okay? So give the standard error of the slope. And then interpret in context. If we repeat the RA, the random assignment, many times, the slope of the sample regression line would typically vary by about 0.0002. And this is a long definition from the slope of the true regression line. Predicting flight time from drop height. So part B says find the critical value for a 95% confidence interval for the slope of the true regression line. Then calculate the confidence interval and show your work. We don't have to test conditions or anything, and it's all pretty much in your calculator. At least for getting the critical value. So how do we get the critical value? Remember, it's T. So to get critical value, we're going to do inverse T. We want 95% confidence. So my area is subtract that from 100, divide it by 2. So 0.025. And then what are my degrees of freedom? $68. Why is it 68 this time? Very good. N minus 2, we had 70 helicopters. Subtract 2 is 68. So watch that right there. We had 95% confidence. So we subtract that from 100, which is 5, and then divide by 2. So it'll be 2.5 or 0.025. This will give you a critical value of 1.995. Our formula says B plus or minus T star standard error of B. There is a way to do this in your calculator. The only problem is you have to put all the data in. So on this one, you have to do it like this, okay? So on this one, you have to do it like this. I'll show you on the calculator when we get some data set that we want to spend time putting in. All right. So your B part right here, think about this opposite of like y equals mx plus b. That's what you're seeing, except for you're seeing y equals b plus mx. Does that make sense? We always write it backwards in stats, and I don't know why. So this is your constant. So it's like your y-intercept. That is coming from your drop height constant or your coefficient. So this part, it should be, sorry, this part up here. Drop height coefficient, which is B. Mhm. All right. So then our little b in our table or in our Minicut output was 0.00572444. We have plus or minus, our T star was 1.995. And then our standard error of B was 0.0002018. When we put that in the calculator, we get an interval of 0.0053218 to 0.061270. C says interpret that interval in context. We are 95% confident that the interval blah, 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 captures the slope of the true regression line, again, right here, true regression line relating drop height. Sorry, I can't spell today. And flight time. So just wanted to write all the way out for you. And then D, it's just bringing back all these things again. So explain what the meaning of 95% confident means in context. This is a long It's like a paragraph. Okay, so just forewarning you. If we repeat the experiment many times, and use the method in part B, to construct a confidence interval each time. (95% of the resulting intervals will capture the slope of the true regression line relating drop height and flight time. Any part of this, could you leave out the use method in part B? That's about all you can leave out. If we repeat the experiment many times to construct a confidence interval, 95% of the resulting intervals will capture. So you can leave out the method in part B or whatever.
Hey, I gotta go to practice. Is that all right?
No,
It's not.
what time are y'all practicing?
I gotta leave now.
Y'all practicing at 3:30? I think you need to talk to your coach about that. I definitely need you till 3 o'clock. That's when I try to finish. You can go today, but I would definitely have a conversation about that.
All right.
All right. Confidence interval for a slope. Everyone knows that cars and trucks lose value the more they're driven. Can we predict the price of the used Ford F-150 Super Crew 4x4 if we know how many miles it has on the odometer? A random sample of 16 used Ford F-150 Super Crew 4x4s was selected from among those listed for sale on autotrader.com. The number of miles driven and price in dollars were recorded for each of the trucks. Here are the data. So we've seen this data before. This is nothing new. Okay. What they want you to do, and I'm going to put it up here so it takes less space, is we're going to construct a 90% confidence interval for the slope of the population regression line. Same thing that we just did. We're just at 90% confidence instead of 95. If we do a state plan, do conclude with this in the state for confidence interval. You're just restating what you're doing. 90% confidence interval for blah, 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 blah. I'm not going to make you write it all out, but that's what you would do in the state part. Same thing in the plan that we always do. We're going to check conditions. We're going to do the liner. This will be much shorter than the last ones that we did. Okay. So L stands for linear. Can you tell me one way that we know it's linear looking at these graphs? Yep. No clear pattern. Perfect. What else could you have said? What about a scatter plot? It's linear. Okay. So whichever one they give you, it doesn't matter. All right. What about I? Independent. Did we take a random sample? Yeah, as long as we took a random sample, it's the 10% condition. We had 16 trucks times 10 is 160, which is definitely smaller than the population. So very good. All right, N. This one's a little bit weird. I hate histograms on this. This is why I hate the histograms. So you could put them in, they gave you the data. You could put it in and make a box plot and talk about the box plot as long as you show it on your paper, okay? But this looks kind of crazy to me. Okay, to me, it doesn't look like the other one. The other one was clear cut, normal, single peaked, whatever. This one is the exact same way. It's roughly symmetric. Single peaked. And that would be, this is your peak up here. And no outliers. There's no gaps, there's no craziness. Same thing for equal SE, sorry. If you look at your scatter plot, it's there's no like outlying residual plot. Like there's not one that's really high or one really low. It's all pretty much the same. So if you look at this, it's not like they're all down here and this one's way up here. Does that make sense? Everything is very equal. So that's what you're looking for. So this is going to say scattered around. Residual equal to 0. And then R, is it random?
Yeah.
We had a random sample. We have 16 pickup trucks. Or Ford F-150 full of whatever. All right. If you need more space, there's more space on the next page. I'm just going to try to keep it here, okay? So with our do, what are our degrees of freedom going to be? 14. 16 minus 2 is 14. We're going to do our inverse T with our area equal to 0.05. Degrees of freedom are 14. Why is it 0.05? 90 subtract from 100 is 10. Divided by 2 is 5. Which gives you a value of 1.761. We have our mini tab output, so we don't have to do any work. We don't have to put these in because we have it right here. What's your first number going to be? Plus or minus 1.761 times. What's your second number going to be? Perfect. That gives you an interval of negative 0.21744 to negative 0.10840. And then I've already given you the long conclude. We are 90% confident that the interval captures the true slope of the population regression line relating miles driven to price. Right. When we flip this over, you'll see that the only thing, that's where I was saying you had extra room for that. We will do this, just not right now. Okay, I'm not making you put in all those values. You're going to go into stat, your test, and it's going to be a lin reg, it's close to the bottom, T interval. So what I'm gonna do is stop there. And then tomorrow we'll do that check your understanding so we can refresh where to find those numbers. I'm gonna show you how to put it in the calculator as well. Got it? And we'll finish 12-1 tomorrow, and then on Thursday, you'll have that test. Everybody good? All right. Zoomers.